The Big Bang theory has impacted our understanding of the universe, establishing the foundation for contemporary cosmology grounded on Einstein's theory and what is acknowledged as conventional cosmology. During the Big Bang, the cosmic era begins with the bang, expansion, the origin of all matter, space, and energy, around 13.8 billion years ago. This occurrence resulted in the huge cosmos that we now view. But recent advances in cosmology indicate that it is possible the Big Bang was not the ultimate source. Rather, there may have existed something before the Big Bang that was equally crucial in the formation of the cosmos as we now understand it. It is referred to as the cosmic inflation epoch, one of the most alluring aspects of contemporary cosmology. According to this theory, prior to the Big Bang's hot, dense condition, the universe experienced an exceptionally quick exponential expansion. Throughout this period, the universe's size grew at a remarkable speed. To show how severe this growth was, if the cosmos had less mass than an atom at the beginning, it would have grown to a size more than the entire observable universe within a nanosecond, specifically, in millions of millions of millions of millionths of a second. This brief span of rapid expansion was essential to forming the cosmos. When inflation stopped, the expansion's energy source was sent into space, where it heated up, creating the matter particles that include everything we see now. In many models, inflation is the precursor of what is now known as the Big Bang. But although the inflation hypothesis is widely acknowledged, there are still many unanswered issues in cosmology. For example, we have yet to identify the factors that caused inflation, how long it lasted, or what prompted it to cease. These are some of the most compelling unresolved issues in cosmology, and resolving them is essential for a more thorough understanding of the beginnings of the cosmos. Prior to inflation, the cosmos was a very dense, tiny point of substance often called a singularity. The ensuing expansion eventually resulted in the creation of atoms, stars, galaxies, and molecules. While the notion that the Big Bang marked the start of everything is attractive, contemporary cosmology suggests a more complex picture. According to theories, the universe experienced a time before inflation. Following the Big Bang, the universe grew exponentially, increasing in size at least 80 times. This rapid expansion was driven by an unknown energy source that dispersed throughout empty space. After inflation stopped, that energy was transformed into particles, heating the cosmos, leading to the hot, dense condition we refer to as the Big Bang. Despite being cold and empty, the inflationary stage laid the foundation for the development of the cosmos and all material we see today. One of the most speculative concepts in modern cosmology is the idea of eternal inflation. This theory suggests that inflation continued everywhere simultaneously, rather than stopping all at once. It ended in various areas, resulting in several distinct zones or bubbles, each of which may exist as a separate universe. Indeed, the cosmos we observe could be just one of these patches. According to eternal inflation, there may be an endless number of such universes, each with its own set of physical laws and constants. This leads to the idea of the multiverse. Our world might be merely one of a large, or possibly infinite, number of universes. If this hypothesis is accurate, it may help explain why life is so ideally suited to our cosmos. In every conceivable multiverse scenario, there could be a range of physical laws. We just happen to reside in a region where the conditions are ideal for the formation of stars and for vital components such as carbon and oxygen to appear. In spite of beliefs like the multiverse and eternal inflation, the notion of inflation itself is backed by compelling empirical evidence. The cosmic microwave background, CMB, the oldest light in the universe, provides proof. The CMB was released about 380,000 years after the Big Bang, when the cosmos had cooled sufficiently for atoms to form. The universe became transparent at that point, and this light has been traveling through space ever since. Research on the CMB allows cosmologists to effectively take a baby picture of the universe. This light provides clues about the early cosmos. Among the most significant discoveries came from the European Planck spacecraft, which took detailed images of the CMB. These pictures revealed tiny variations in temperature in the early universe, consistent with forecasts made using inflationary theory. Experimental validation reinforces that inflation is more than speculative, it is an essential part of our understanding of the universe's beginnings. Understanding the Big Bang and its aftermath requires merging two of the most crucial ideas in contemporary physics, Einstein's general relativity and quantum theory. General relativity explains the large-scale structure of the universe, including the behavior of planets, stars, and galaxies. Quantum theory, on the other hand, clarifies the behavior of the tiniest particles. To address fundamental cosmological questions, such as what space and time really are, and how the universe began, scientists had to develop a hypothesis that unites these two frameworks. A unified theory could help us comprehend not only the Big Bang but also the circumstances that led to it. One unexpected feature of the universe is its vast size. There are about 47 billion light-years of observable objects from our perspective. This means the observable universe is about 94 billion light-years wide. At first, this may seem contradictory, since the age of the cosmos is only about 13.8 billion years. How can we see more than 13.8 billion light-years? The answer lies in the fact that the universe has been expanding. As it expands, the distance between objects increases, allowing us to see farther than light could travel in a static universe. Most experts believe the cosmos is far larger than what we can observe. It's possible that the entire universe is infinite, and the observable universe is just the portion we can see. Light has existed since the beginning, but there may be regions of the cosmos we will never be able to detect. Even though the universe may not have boundaries, a lingering question remains: what lies outside the universe? Most scientists believe this is a flawed question. If the universe is infinite, there is no outside. And if it is finite, then discussing an outside may not make physical sense. Space and time are features of the universe itself. Thus, asking what existed before the Big Bang or outside the cosmos may be as pointless as asking what lies north of the North Pole. Still, such questions push the boundaries of human curiosity and motivation. Recent advances in theoretical physics have led to new ideas aimed at addressing these profound puzzles. One such framework is string theory, which posits that the universe is made of tiny vibrating strings of energy, rather than point particles. It also suggests the existence of additional dimensions beyond the familiar three of space and one of time. These hidden dimensions may be curled up at such small scales that they remain undetected with current technology. Another emerging idea is loop quantum gravity, which attempts to merge quantum mechanics with general relativity. According to this theory, space itself is quantized, composed of tiny discrete units, similar to gravity. However, the discovery of dark energy in the late 1990s upended this assumption. Instead of slowing, the universe's expansion is accelerating, an observation supported by the redshift of distant supernovae and confirmed by multiple independent measurements. Dark energy is thought to make up about 68% of the total energy content of the universe, yet its nature remains one of the biggest mysteries in cosmology. Some theories describe it as a property of space itself, an inherent energy density that doesn't dilute as space expands. Others propose more exotic explanations, such as quintessence or modifications to Einstein's general relativity. The fate of the universe. The presence of dark energy has profound implications for the ultimate fate of the universe. The current leading scenario is known as the heat death or big freeze. In this model, as the universe continues to expand, galaxies will drift apart until they become unreachable. Stars will burn out, leaving behind cold remnants like white dwarfs, neutron stars, and black holes. Over immense timescales, even black holes will evaporate via Hawking radiation. Eventually, all matter will decay or become so spread out that the universe reaches a state of maximum entropy, cold, dark, and empty. Other possibilities include the Big Rip, if dark energy becomes stronger over time, tearing space apart, or a Big Crunch, if expansion reverses, but these are currently less supported by observational data. Unanswered questions. Despite remarkable progress, many questions remain. What is dark energy? What caused the initial inflation? What existed before inflation or the Big Bang? Can general relativity and quantum mechanics truly be unified? Closing thoughts. Modern cosmology sits at a thrilling intersection of theory and observation. With instruments like the James Webb Space Telescope, gravitational wave detectors, and advanced particle colliders, we are closer than ever to unlocking the secrets of the cosmos. Still, every answer leads to deeper questions, and the ultimate nature of reality continues to inspire awe, curiosity, and discovery. Matter's gravitational attraction meant there was perhaps a chance that the cosmos could cease to grow and start crumbling under extreme pressure. However, it seems that dark energy is increasing the distance between the universes rapidly. If this acceleration continues, the universe will continue to expand indefinitely, ultimately arriving at a stage where the distance between galaxies is so great that they drift apart from one another. In this scenario, the cosmos would cool off. The stars would burn away, leaving behind a black and empty void. All matter and the universe would divide, fragment, and ultimately deteriorate, a result referred to as freeze death or heat death of the cosmos. The narrative of the cosmos, from its beginning to its end, is one of the most profound and intricate scientific tales. While we have learned a great deal about the origins of the cosmos via inflation theory and the investigation of the cosmic microwave background, there are still many unsolved questions. What caused inflation? What prevented it? Why does something exist outside of the visible universe? How many alternative multiverses exist? As scientists, we keep exploring the cosmos using ideas and cutting-edge technologies that blend quantum mechanics with general relativity. We will surely continue to uncover more. The quest to comprehend the cosmos is continuous, and every new finding brings us closer to answering the ultimate questions about our existence. Examining the universe's structure and beginnings is not only a scientific undertaking, it also raises philosophical questions about reality, existence, and our role in it. One of the main topics in cosmology is comprehending dark matter, which is believed to make up around 27% of the mass and energy content of the cosmos. Dark matter is not like regular matter. It neither produces, reflects, nor absorbs light, making it undetectable, only discernible by its gravitational effects on visible matter. Learning about dark matter is essential to understanding the formation and dynamics of galaxies. Observations and experiments have provided further insight into the characteristics of dark matter. Although its precise nature is still unknown, several candidates have been suggested, including weakly interacting massive particles, WIMPs, and actions. However, no concrete proof of dark matter particles has yet been found. But the search continues. Scientists are combining astronomical observations, ground-based experiments, and computer simulations to model how dark matter influences cosmic structure. Another vital area of inquiry is dark energy, an enigmatic force accelerating the universe's expansion. Dark energy comprises about 68% of the mass energy content of the universe. Its discovery was surprising and has led to several explanations, including the cosmological constant and dynamic fields like quintessence. Understanding dark energy is essential, as it will determine the ultimate fate of the universe. Researchers are examining whether dark energy stays constant over time or varies, and how it affects the formation of celestial structures. Alongside dark matter, the study of energy and cosmic structure formation provides insights into the evolution of the universe. Measurements of the cosmic web, networks of galaxy clusters and filaments, have shown how matter clumps under gravity, resulting in today's complex structures. Supercomputer simulations help scientists understand how these structures formed over billions of years and continue to evolve. The intersection of cosmology and astrobiology is also expanding. Scholars are investigating the conditions that support life beyond Earth, especially in the search for extraterrestrial life outside our solar system. The number of exoplanets found circling distant stars has increased dramatically in recent years. Some of these planets lie in habitable zones where liquid water might exist. By studying these distant worlds, researchers hope to better understand the possibility and nature of life elsewhere in the universe. Moreover, physics plays a crucial role in cosmology. The pursuit of a unified theory that merges quantum mechanics and general relativity remains a challenge for physicists. Theories such as string theory and loop quantum gravity aim to bridge this divide and potentially explain phenomena like black holes and the origins of the universe. Technological advancements are also enhancing our ability to observe and understand the cosmos. Instruments like the James Webb Space Telescope are revolutionizing our understanding by providing unprecedented data on distant galaxies and cosmic events. With every new observation, we piece together more of the universe's puzzle, its creation, development, and ultimate fate. In summary, the study of the cosmos is both a broad scientific investigation and a deeply intellectual endeavor. From the fundamental forces shaping cosmic structures to the search for alien life, our pursuit of knowledge reflects humanity's profound curiosity about the universe. As we seek answers to these fundamental questions, we not only gain insight but also deepen our appreciation for the universe's vastness and complexity. The connection between cosmological theory and observation is vital. Technical advances, such as sophisticated detectors, machine learning, and advanced algorithms, are improving our ability to analyze astronomical data. These tools help researchers sift through enormous datasets, uncovering patterns that may lead to new insights into cosmic phenomena. One particularly exciting field is the study of gravitational waves, ripples in spacetime caused by cataclysmic events like black hole or neutron star collisions. The discovery of these waves has opened a new observational window into the cosmos. Studying them provides insights into extreme conditions and allows scientists to test gravitational theories with unprecedented precision. Additionally, the concept of cosmic time is fascinating. Unlike our everyday experience of time as linear and uniform, cosmic time is shaped by the universe's expansion. This raises profound philosophical and scientific questions. Is time absolute? Does it depend on the observer's motion and position? These inquiries underscore the complexity of cosmic study. Another crucial area of focus is the formation of the first galaxies and stars, referred to as the cosmic dawn. Understanding this epoch sheds light on how the cosmos transitioned from a hot, uniform state to the intricate structures we observe today. High redshift observations of distant galaxies offer clues about the processes that occurred during this formative time, helping scientists construct a timeline for cosmic evolution. This timeline of cosmic evolution not only enhances our understanding of the universe's past but also helps refine predictions about its future. The epoch of reionization, for instance, marks a critical period when the first luminous sources ionized the surrounding hydrogen gas, dramatically changing the universe's transparency and structure. Studying this era allows astronomers to trace the influence of the first stars and galaxies on the intergalactic medium. As observations become more refined, especially with tools like the James Webb Space Telescope and future missions such as the Nancy Grace Roman Space Telescope, we expect to uncover even earlier and fainter objects, pushing our knowledge further back toward the Big Bang itself. In parallel, the role of neutrinos, elusive, nearly massless particles, is being actively investigated. These particles, which rarely interact with ordinary matter, hold crucial information about the early universe and may also play a part in explaining the behavior of dark matter and energy. Experiments like IceCube in Antarctica and the Deep Underground Neutrino Experiment, DUNE, are at the forefront of this effort, offering potential insights into both particle physics and cosmology. Furthermore, the concept of the multiverse, once considered purely theoretical, is gaining more scientific attention. Inflation theory, string theory, and interpretations of quantum mechanics have all opened doors to the idea that our universe might be just one of many. Though we currently lack the tools to observe other universes directly, researchers continue to explore indirect evidence, such as anomalies in the cosmic microwave background or unexplained fluctuations in spacetime. As scientific models grow more sophisticated, they also become more interdisciplinary. Cosmology now draws heavily from fields like thermodynamics, information theory, and even biology, particularly in discussions about the anthropic principle, the idea that certain conditions in the universe appear finely tuned for the existence of life. Whether this fine-tuning is coincidental, necessary, or evidence of a larger multiverse remains one of the most hotly debated topics in theoretical physics. On the philosophical front, our expanding comprehension of the cosmos forces humanity to confront age-old questions with new perspective. What is our role in this vast universe? Are we unique? Are we alone? And if not, what forms might alien life take, and how would we recognize or communicate with them? These questions echo beyond science, touching on ethics, religion, and the essence of consciousness itself. Some scientists and thinkers propose that consciousness might even be a fundamental aspect of the cosmos, interwoven with space-time, matter, and energy in ways we have yet to comprehend. As our instruments and theories grow more powerful, so does our sense of wonder, and our responsibility. Exploring the cosmos is not merely about satisfying curiosity. It's also about preserving our planet, understanding the forces that govern our existence, and preparing for a future in which humanity may one day become a multiplanetary, perhaps even interstellar, species. In this grand pursuit, every discovery, no matter how small, adds a piece to the vast puzzle. From dark energy's invisible push to the faint glow of the first stars, from gravitational waves rippling through spacetime to potential signals from distant civilizations, the universe continues to speak. And we, with our growing tools and evolving minds, continue to listen.